galactic systems colliding before they'd physically exist, and local planets breaking basic chemical rules. What makes this failure so significant is that the telescope was not built to find contradictions. It was built to design its optical systems, calibrated its detectors, and programmed its observing schedule. They were building a tool that would confirm and refine existing theories. Instead, with each new dataset returned across the void of space, the James Webb Space Telescope at a specific region called the JADE's Origins Field. They captured light from an object designated metric known as redshift. Researchers pinpointed its location in time. The data places this object just 300 million years after 1 million years means on a cosmic scale. Our universe is currently estimated to be approximately 13.8 billion years old. The period in question represents roughly 2% of the total age of the cosmos. In absolute terms, 300 million years, it is barely enough time for a single generation of massive stars live their brief violent lives and die in supernova explosions. The universe at that age was not a place of mature structures and organized complexity. It was a turbulent, hot, rapidly expanding. Any structure existing that early in the universe should be a primitive, newly forming galaxy. It is supposed physical measurements provided by JWST immediately broke that expectation. The object is exceptionally bright and unusually compact, spanning about 1,600 light-years across. If astronomers classify this object as a standard galaxy, its extreme luminosity implies that it contains a stellar mass equivalent to hundreds of millions of our suns. That creates an immediate mathematical problem. For a galaxy to accumulate that much mass in only 300 million years, it would need to convert available gas into stars with near-perfect efficiency. To put that in perspective, typical gas clouds to star formation is not an instantaneous process. It requires gas, fragment, contract, and eventually ignite. Each of these steps imposes a physical speed limit. There are minimum timescales governed by the fundamental constants of nature. The object is too massive and too bright for its age, and no straightforward modification to existing theory closes the gap entirely. Because the standard galaxy model is difficult to reconcile with the brightness and mass, some researchers, including a team led by Catherine Fess, have utilized JWST's near-infrared spectrograph to propose an alternative theory. Spectroscopy allows scientists to break down the light from an object into a detailed barcode, revealing the physics for over a century. The blurring and filtering effects of Earth's atmosphere. The technique reaches an entirely new level of precision. If JADE's GSE 140 were a dense cluster of young hot stars, the spectrum would show a chaotic mix, overlapping light signatures and intense stellar winds, the combined thermal emission of billions of burning nuclear furnaces, each producing their own JADE's GSE 130, revealed a really specific and uniform profile. The most critical piece of evidence, DIP acts as a definitive fingerprint. It proves the presence of vast quantities of singly ionized helium existing in a cool, diffuse state. Signature. Stars create complex, overlapping spectroscopic profiles, each one bleeding into the next, creating a messy background of continuous radiation punctuated. Uniform signal detected here. The object is too uniform and the temperature profile is too cool for standard stellar mechanics. Solution tends toward complexity. A signal this clean, this dominated by a single diagnostic feature, suggests a physical object of unusual simplicity and uniformity. Based on the physical dimensions required to produce that specific light profile, a supermassive dark star is unlike anything currently existing in the cosmos. It is a singular giant puffy cloud made exclusively of pristine hydrogen and helium. It does not have a dense burning core like our Sun. Instead, It is highly diffuse, potentially stretching across a diameter larger than our entire solar system. To understand the scale of this claim, consider that our solar system, from the Sun to the outermost reaches of the Oort cloud, extends across distances measured in light years. The idea that a single coherent object, bound by gravity and held in a stable non-fusing state, could span that entire range stretches every intuition built from studying ordinary stellar physics. The most vital detail hidden in the 1640 angstrom dip is the heat source, because the object is so large it from collapsing under its own gravity. The spectroscopic data align perfectly with theoretical models of dark matter annihilation. This means the object is gathering invisible dark matter particles into its center, where they collide and annihilate, producing the outward radiation pressure needed to keep the star inflated and glowing brightly. Dark matter annihilation largely as a mathematical curiosity, an interesting thought experiment about exotic conditions that might have existed only in the earliest moments of cosmic history, for a specific object captured in the telescope's data. The observation is locked. JBUST looked at a target, gas-powered, entirely by the destruction of dark matter. Astrophysics relies on a very strict set of rules for a star is born. As the cloud shrinks, the pressure and temperature inside the core rise exponentially. Eventually, the core gets so hot and so dense that hydrogen atoms, it releases an enormous amount of outward energy, which pushes back against the inward crush of gravity. When the inward pull and the outward push balance out, the star achieves hydrostatic equilibrium. It ignites and becomes a stable burning object like our Sun. This entire sequence strictly requires the gas cloud to become incredibly dense. There is no room in this framework. The cloud collapses far enough to trigger fusion, or it disperses back into the interstellar medium. A stable intermediate state, a cloud large enough to be called a star, yet never hot enough to fuse, requires precisely the kind of energy injection that dark matter annihilation would provide. The existence of a supermassive dark star would completely shatter this sequence. To understand why this discovery breaks the laws of standard cosmology, we have to look at the mechanics of dark matter carefully. Gravitational skeleton. It pulls regular gas together to form galaxies, but otherwise does not interact with normal matter or with itself. It is considered completely collisionless. This property is actually fundamental to the success of the standard. Or with regular matter, the structure of the universe would look very different from what we observe. The large-scale web of filaments and voids that traces the cosmic distribution of matter depends critically on dark matter behaving as a non-interacting gravitational scaffold. A dark star requires dark matter to behave very differently. For an object like Jade's GSZ 140, as adjunctively interfere with the gravitational collapse of the hydrogen gas. Theoretical physics proposes that dark matter consists of weakly interacting massive particles, often called WIMPs. When these this annihilation process generates pure thermal energy. Here is the physical impossibility embedded within that sequence. Pushes outward, stalling the collapse of the cloud, before it can ever reach the density required for nuclear fusion. The object becomes a massive glowing balloon of gas suspended in a permanent state of thermodynamic interruption. It never becomes a real star. It just sits there feeding on dark matter merely as an observational discrepancy, but as a fundamental theoretical one. Current simulations dictate dark matter in the early universe simply was not dense enough, nor did it possess the correct interactive properties to stall the collapse of giant gas clouds. The accepted physics state influencing the thermodynamic evolution of that gas. That picture, if the dark star interpretation holds, needs to be self-annihilate and generate this outward pressure. Our fundamental understanding of early universe thermodynamics requires If supermassive dark stars were a general feature of the early universe, they would have dominated its energy budget during the first few 100 million years, and potentially seeded the supermassive black holes we find at galactic centers today. The collapse of a dark star's form. This would help address another separate but related mystery. Why the universe's first black holes are so much. A dark star can continue pulling in surrounding gas and growing indefinitely as long as it has a steady supply of dark matter fuel in its core. They can reach sizes, structures this massive to form within the first 300 million years under conventional assumptions. The available material in that era, while simultaneously maintaining a core of annihilating matter, requires a mechanism of mass accumulation that astrophysics currently cannot fully explain. This discovery suggests that the first structures in the universe might not form through actively dictated the physical state of regular matter, keeping it hot, diffuse, and incredibly bright long before the first true one that no model currently accounts for, and one that changes the story of how everything we see today came to be. When scattered across the background of the early universe, specifically in the era roughly 600 million years after Big Bang, were hundreds of highly compact bright red sources of light. The astronomical community informally named the little red dots. The red color is a product of cosmic light from the early universe spends so long traveling through expanding space that its wavelength is stretched from the visible range deep into the infrared. The JWST is uniquely equipped to detect this infrared light, which is precisely why astronomers initially interpreted these bright sources as standard galaxies. That interpretation immediately how many stars it contains. To shine as brightly as the little red dots, these objects had to be packed with an impossible number of 14 billion years to assemble that much mass. Finding objects this heavy existing just a few 100 million years after the universe began broke all accepted models of galaxy formation. The scientific community quickly started calling them universe breakers. The label was hyperbolic in tone but not in substance. Every simulated timeline of cosmic structure for telescopes, and they had always matched. Now, confronted with data from an observatory capable of seeing further, researchers more than just pictures, they needed to dissect the light itself. They used JWST's spectrographs to collect its component wavelengths, creating a physical barcode that reveals exactly what is generating the illumination. If the little red dots were indeed massive galaxies, a dense, complex, multi-layered signal built from the combined emission of stellar populations at different ages, collection of stars, the researchers found a very specific V-shaped light profile. This shape alone was unusual enough to prompt careful scrutiny. In astrophysics, spectral profiles carry the physical history of the object that did what astronomers call broad-Balmer emission lines. These lines are definitive indicators of physical movement within a celestial object. When gas is moving violently, the Doppler effect smears those lines out, making them broad. The width of an emission line is therefore a gas inside them was orbiting at speeds exceeding 2 million miles per hour, approximate 3.2 million kilometers per hour. Orbital dynamics simply do not work. Even an entire galaxy, with its combined gravitational pull of hundreds of billions of stars, does not typically generate internal gas velocities at the gravity to whip gas alternative to the massive galaxy theory. The little red dots appear to be exceptionally tiny, ultra-dense environments. The black hole is wrapped in a thick, dense sphere of cold gas. As the black hole consumes the material, gas envelope to glow brightly, scientists are now classifying these peculiar objects as black hole stars. They are tiny, highly concentrated. Was never coming from billions of stars. It was coming from a single point of catastrophic gravitational consumption, an solar system. In the modern universe, supermassive black holes and their host galaxies, it dictates that the central black hole will always contain roughly 0.1% of the total stellar mass of the entire galaxy. If the galaxy grows, the central flawlessly for nearly every mature galaxy we can observe in our local cosmic neighborhood. It has been confirmed in galaxy after galaxy across a wide range of sizes and type linked each the other through feedback mechanisms involving the energy released during accretion. The little red dot holes inside these compact gas clouds, the numbers did not align with the surrounding structure at all. Instead of being a tiny fraction of their host, others appear to be equally as massive as the entire surrounding system. This is a severe violation and the standard ratio allows. The feedback mechanisms that were supposed to keep black hole and galaxy growth synchronized, clearly explaining how a black hole can interact. Material spirals inward, it compresses, heats up, and releases intense radiation. This radiation pushes upward against the outward radiation pressure overpowers the inward gravity. The black hole literally pushes its own food away, choking off feeding to become supermassive. Think of it as analogous to trying to pour water into a funnel faster than the narrow opening allows point. Standard cosmological models assume early black holes started as the collapsed cores of the very first star. If the Eddington limit holds true, the cosmic timeline simply does not offer enough time for that much controlled feeding to occur. Models for the early universe. They must instead theorize a completely unverified process called direct collapse. This theory suggests massive black hole seeds, weighing up to 100,000 solar masses. Even that theoretical shortcut, drastic as it is, only partially solves the problem. The seeds are larger, but the feeding still takes time, and the Eddington limit still applies. Physics cannot explain how a black hole galaxy remained completely stunted. The two objects are supposed to grow together over billions of years, kept in balance. The JWST data proved that the black hole somehow won the evolutionary race before its host galaxy even finished forming. A black hole is not simply a dense gravitational object. It represents the maximum entropy configuration allowed by known physics of its event horizon rather than its volume, an outcome that defies conventional thermodynamic intuition and underlies the long-standing information paradox. Explorative to their host galaxies therefore raises a deeper question. Could the early universe have temporarily favored the rapid formation of maximum? If so, this would imply a reversal, at least in certain regimes, of the conventional bottom-up narrative of cosmic evolution. That in the earliest epochs, the universe briefly prioritized the creation of information maximally dense objects before establishing the large-scale architecture from the distant edges of the early universe to a localized planetary system roughly 2D light years away in the constellation Sextans. The central star marks it as a member of the galactic thick disk population, a relic of an earlier of star formation that predates the heavy element Henri, making it roughly twice as old as our own sun. In cosmic terms, it formed when the universe was still young, long silicon and iron that now make up the rocky planets of our own neighborhood. Orbiting incredibly close to this ancient star, this planet are extreme. The distance between the stars. That is roughly 1/40th of the distance between Mercury and our Sun. Mercury itself is considered a hellish more energy per unit area than Mercury does, and it has been receiving that energy for 10 billion years. Because it orbits in such tight proximity, the gravitational mechanics dictate that the planet is tidally locked. One hemisphere faces the star and Terminator line is a region of eternal twilight and extreme atmospheric dynamics, where winds driven by the enormous investigate the physical nature of this world. Researchers utilize the near-infrared strategy required hours. This extended window allowed the instruments to capture nearly 4 complete orbits of the planet. For context, 37 hours of uninterrupted observation time on JGUST is an extraordinarily valuable investment of the telescope schedule. The fact that this target was allocated that much time reflects thus the scientific significance assigned to understanding this specific planetary system. The primary goal of this observation was to measure the thermal emissions radiating from the permanent day side of the exoplanet. The telescope achieved this by recording the total infrared brightness of the star and it during a secondary eclipse. The remaining data provided a direct temperature readout of the planet's illuminated surface signature permanent day side to an expected temperature approaching 4,900 degrees Fahrenheit, approximately 2,700 degrees Celsius. The rock would absorb the energy and radiate it directly back into space, creating a sharp spike in the infrared. Predicted that expectation. The day 760 degrees Celsius. Still hot enough to melt solid rock. It is significantly cooler than the bare rock model. This precise drop in temperature, combined with the missing wavelengths, provides the physical evidence needed to identify the planet's surface conditions. The only mechanism capable of lowering the dayside temperature by that much, a dense, volatile, or rich atmosphere. A thick envelope of gas acts as an insulating and redistributing layer. It absorbs a portion of the incoming near-infrared light and utilizes high-speed planetary winds to carry the thermal energy away from the day side and distribute it around to the night side. The telescope did not just find a hot rock, it confirmed the presence of a stable, thick atmosphere. After 10 billion years of extreme irradiation, it is almost physically incomprehensible. Planetary physics relies to its host star. The incoming radiation severely heats the gases in the planet's atmosphere. As a gas heats up, its gravitational field cannot hold on to those fast-moving molecules. They reach escape velocity and bleed off into the vacuum of space. Violet and X-ray radiation acts like a blowtorch. It is highly efficient at destroying atmospheric layers. Because TOI 561b is a super-Earth, it does not possess the massive gravitational anchor of a gas giant like Jupiter. Under that level of stellar bombardment, the star should have blasted away all surrounding gases during the earlier stages of the planet's life. We also point-blank radiation. The physics state unequivocally that this world must be a barren, scorched piece of rock. Finding atmospheric retention are missing a massive variable. Since the planet cannot physically hold on to its original primordial atmosphere over that immense time span, helium, it formed with, those light elements were stripped away eons ago. Therefore, it must be a secondary atmosphere. More importantly, the planet must be generating this new atmosphere in real time. This process is not without precedent. Both Earth and Venus lost their primordial hydrogen-helium envelopes early in their histories and subsequently developed secondary atmospheres through volcanic asteroidal delivery. However, the present case differs dramatically in both rate and duration. While atmospheric regeneration is understood as a geological process, typically occurs gradually, with volcanic emissions building up over long timescales. In contrast, TOI 561b must sustain atmospheric production at a far higher to redistribute heat across the planet. The replenishment rate must continuously match or exceed the rate of loss. The physical mechanism sun-facing side of the planet exists at such an extreme temperature. Crust cannot exist in a solid state. The entire illuminated hemisphere is a boiling sea of magma. This liquid rock acts as a planetary engine. Deep inside the world, the magma continuously exhales heavy gases, injecting them directly into the sky above. We are likely looking at an atmosphere composed of vapor molecules, require significantly more energy to reach escape velocity compared to hydrogen. This creates a violent perpetual cycle of destruction and rebirth. The star burns away the top layer of the atmosphere, while the boiling magma ocean continuously outgasses fresh material at the bottom to replace it. Current planetary models did not account for a stable atmosphere on this world, proves that planets we previously dismissed as dead rocks can actually host incredibly complex, active to simulate. Researchers directed the James Webb Space Telescope to observe a specific coordinate corresponding to a redshift. The initial deep field images revealed a dense, irregular concentration of light. By separating the light sources, named this formation Geboestes Quinte. These 5 galaxies do not simply exist in the same general region. The data confirms are completely entangled. The outer edges of the galaxies are tearing into one another, pulling billions of tons of matter out of their standard orbits. The tidal forces at work in such a collision are staggering. Stars are not colliding directly, because the distance between individual stars is so vast that even when galaxies merge redirected on an enormous scale. The collision triggers massive bursts of star formation in the compressed regions where gas clouds are slammed. Researchers needed to look at the space between the galaxies. They utilized a specialized mode on the near-infrared the entire for every single square in that grid simultaneously. This technique generates a 3-dimensional of specific chemical elements across the entire collision zone, providing not just a snapshot of what is present, but a continuous structure of gas wrapping around all 5 galaxies. This gas forms physical bridges connecting the individual galactic cores. As the galaxies orbit and crash together, they drag this gas along with them. When the researchers isolated the chemical signatures within this gas network, were detected across the entire field of view. The data prove that oxygen is not confined to the star forming the oxygen outward. It is being thrown to the cold void separating the galaxies. The data cube also measured the velocity of this gas. By tracking the Doppler churning and mixing at high speeds as the 5 gravitational wells pull at it simultaneously create a roiling, supersonic environment of is mass, a physical area significantly larger than our own Milky Way. The observation provides a direct visual record of a 5-part galactic pileup, actively redistributing heavy elements across a massive sector of the early universe. Cosmology maps the early universe as a vast, sparsely populated void. Gravity operates at a fixed, predictable speed, 100 million years old. Undisturbed streams of gas, beginning to build up their first stellar populations. Nowhere near the structural complexity required. Gravitational space completely breaks the organization timeline. Gravity did not have time to drag these massive galaxies, in close enough proximity for their gravitational fields to interact require a degree of large-scale structure organization. The true physical impossibility lies in the presence of the oxygen. The Big Bang produced exactly 3 elements. It created hydrogen, helium, and a microscopic of lithium. The early universe contains 0 oxygen. A massive first-generation star must ignite, burn through its initial hydrogen fuel, and start fusing heavier elements through successive stages of nuclear burning. Carbon, neon. This collapse triggers a supernova explosion. That explosion is the only mechanism capable of scattering a small amount of oxygen, a few light years, in single galaxy is one thing. It requires only that a handful of massive stars have had time to live and die within that galaxy. The JWST data show massive quantities of oxygen spread among heavy elements out of a deep galactic gravity. Well, requires an immense sustained physical force. It takes thousands of simultaneous supernovae, firing over hundreds of millions of years, to generate galactic winds powerful enough to blow oxygen, their combined energy exceeding the gravitational binding energy of the gas they are trying to expel. When you add up the time required from the pristine hydrogen gas of the early universe, you need time for them to burn out and die. You need time for their debris to mix with fresh gas and form second-generation stars. You need time for those secondary stars to die and generate outward galactic winds simultaneously. You need time for 5 separate galaxies to physically locate each other and merge. The 800 million year mark on the cosmic timeline is drastically too early for this level of chemical and structural maturity. This specific collision proves that clustered together at a speed that current physics cannot yet easily explain. We are shifting focus away from early universe young star system designated CT Chamaeleontis. The central star is essentially an infant in stellar terms. It is surrounded by a massive swirling cloud of raw gas and dust known as a protoplanetary disk. This massive debris field contains the foundational building blocks required to construct planets, asteroids, and comets. The disk is not a static object. It is a dynamic, actively evolving structure where gravity, radiation, magnetic fields, and thermochemical gradients compete. System orbits a newly formed gas giant named CT Chamaeleontis b. While the planet itself has already gathered the bulk of its mass, its gravitational field is still highly active. It is actively pulling in surrounding material from the main stellar cloud around the planet. Astronomers classify this structure as a circumplanetary disk. This specific tightly bound ring of debris serves a singular purpose. It is the exact location where moons are built. The circumplanetary disk is one of the most for satellite formation. Everything that forms within it will eventually become moons. To analyze the physical properties of this system, researchers operating in the mid-infrared spectral lengths of light simply bounce off the thick dust of a stellar nursery, leaving the interior hidden. Mid-infrared light easily penetrates the dust. When this specific type of light hits molecules in space, it causes them to vibrate. Different molecules vibrate at distinctly direct, highly accurate chemical inventory of the gas, without needing to resolve individual molecules individually. The telescope detects their collective spectroscopic fingerprints and works backward to identify what is present and in what abundance. The scientific team used this instrument to map the chemical makeup of both the massive disk surrounding the Proteus through a Young system. Standard theory: the composition of the protoplanetary disk, because the planet builds its surrounding ring by siphoning material from the larger reservoir. The spectroscopic data returned a massive discrepancy. When the telescope analyzed the primary star-age disk, it recorded standard building materials, water vapor, and basic silicates. It did not record a single. The instruments then targeted the circumplanetary disk orbiting CT Chamaeleontis b. The chemical readout in this localized region was in spectrographs isolated strong, undeniable thermal signatures of carbon-based molecules orbiting the planet. The most prominent and surprising detection within this localized disk and similar disks by JWST was benzene. Benzene is a complex ring-shaped hydrocarbon molecule. It requires very specific physical and a severe environmental split within a single system. The telescope captured a dense concentration of complex carbon molecules, tightly wrapped. Planetary formation operates on a strict principle known as chemical inheritance. A star and its entire planetary system are born from the exact collapsing cloud of interstellar material. Because they share a single origin point, the chemical recipe is star are the only ingredients available for construction. If you want to build a planet or a moon, You must use the materials provided. A young gas giant gathers its building materials by siphoning gas and dust directly from the primary stellar disk. Its gravity acts like a vacuum, pulling. This is a simple one-way transfer of mass. Logic and standard physics dictate that the chemical makeup of the planetary must perfectly match the chemical makeup of the stars down of this supply chain. The primary reservoir feeding the entire system contains no measurable gas-phase carbon molecules of a specific element out of a completely empty reservoir. If the star's disk lacks gaseous carbon, the planet's disk has no physical way to acquire it through standard mass transfer. The presence of benzene magnifies this physical improbability. Hydrocarbon ring, the foundational structure from which many more complex organic molecules are built. Synthesizing benzene in the vacuum of space requires massive directly surrounding a forming gas giant is incredibly cold and heavily shadowed by the planet itself. It lacks the intense ultraviolet radiation. Astrochemical models simply cannot explain this environment. A cold localized disk of debris should not be capable. The mathematics regulating chemical evolution speeds within an isolated system does not allow for this drastic divergence. The carbon had to come from somewhere. Colder outer regions of the protoplanetary disk, regions cold enough to condense volatile carbon-bearing ices onto grain surface, could have been released from the solids and converted into gas phase molecules. But this requires a very specific set of conditions, an efficient inward transport mechanism, a thermal and capable of volatilizing the carbon without destroying the complex molecular structures, and a carbon monoxide or methane. None of these conditions are straightforwardly satisfied by current models. This observation dismantles the idea that moons passively inherit their chemical ingredients. It forces a complete rewrite of how localized systems operate. The data suggests that the immediate environment around a young gas giant is not just a passive collection ring. It must be acting as an independent, highly active chemical factory. It is taking invisible solid carbon locked deep inside dust pebbles, vaporizing it, and rapidly forging complex organics at a speed that astrophysics currently considers impossible. The significance of this discovery extends far beyond the formation of moons in CT Chamaeleontis. If circumplanetary disks can generate complex organic chemistry independently of their host star's reservoir, then the chemical diversity of moon systems throughout the galaxy may be far greater than anyone has imagined. The moons of gas giants, which orbit in diverse young stellar systems across the Milky Way, may each be chemically unique. Each biology, this matters enormously. The building blocks of life as